So we've done a couple of examples. Had you guys do a couple of examples of paying in where we know the monthly payment and how long to get the future value, and then one where we know how much we want to have and figuring out what we require as the monthly payment. And those were all for an ordinary annuity. We also looked up the table value in the book and used that for an ordinary annuity. Now, we used it going one direction, where if we had the monthly payment, what would the future value be? We can also go the other direction of, if we know what our future value is, figuring out what the monthly payment would have to be, or the payment per period would have to be. For example, let's say we need, or we want, $200,000 in 5 years. We figure we can earn 12%. How much to pay each quarter? So first thing we need, what is our number of periods? 5 years times 4 quarters per year is 20 periods. Next, rate per period. Got 12% divided by 4 periods is 3%. So we're going on our table, 20 periods and 3%, which is what? 26.870? Future value of 200,000 before we took the payment and we multiplied by the factor to get the future value. If we have the future value, we're going to divide by the factor. So 200,000 divided by 26.870, we get 7,443.25. So each quarter you'd have to pay almost $7,500 to get that $200,000 in 5 years. The other thing we have not yet looked at is something called an annuity due. We talked about it, haven't calculated with it at all. Remember, an annuity due was where the payment was made at the beginning of each period instead of the end of each period, which meant you had an extra period's worth of interest on every payment. In fact, that extra period worth of interest just kind of builds up and can be done all at once at the very end. You can think of it instead of saying, hey, we're making the payments at the beginning of the periods, what you can do is you can do this. You can say, hey, we're just going to start it out a period early, and it figures out just like a regular ordinary annuity, and then at the end it sits there for an extra period at the end. So all we have to do is we have to add the interest for this extra period at the very end, because the money is at the beginning of the period, it's sitting there for an extra period after all the payments are made. Excuse me. So all that happens is there is a correction factor for the annuity due, and that is times 1 plus the interest rate divided by n. And that's it. This is the power of 1 because it's only one period that we're adjusting for. So let's say that we are going to invest $250 per month. 10% investment for 30 years. Find future value of annuity due. So 250 times 1, 2, 3. 1 plus 10% is 0.10. It's per month, so divided by 12. Close parentheses to the power of 30 years times per month. That's the adjustment factor that's only the power of 1. We still got to do the rest of the formula normally yet. So it's power of 360, 30 years times 12 months a year. Minus 1. Close, divided by open. 0.10, divided by 12, close and close. Well, so far we have done absolutely nothing different. We calculate this all out, we've got the future value of an ordinary annuity. What makes it an annuity due is we add this little factor, times 1 plus 0.10 divided by 12. So this right here, only difference. So let's punch it in. 250 times 123, 1 plus 0.10 divided by 12, close power, 360, minus 1, close, divided by open, 0.1 divided by 12, close, and close. Again, that would end the ordinary annuity part of it. Now for the annuity due, we do times open, 1 plus 0.1 divided by 12, close. $569,831.33. Not so bad. So now if this annuity due has this extra little factor here, how do we use the table to do an annuity due? Well, let's do an example that we could use the table. Just like with the present and future value for compound interest tables, the tables are so limited. You have to have some very, very delicate numbers to make them work. If you don't have those numbers that actually appear in the table, it don't work with a darn. So let's come up with an example that will work with the numbers in the table. So let's say we're going to invest $300 per month. Actually, no, we're going to go $300 per year at 5% for 20 years in an annuity due. So on the table, how many periods? 20. 1 a year. Rate per period? Well, this is per year, it's just a 5%, right? So we're looking at 20 and 5%. Let's go to the next page. $33.066. Look right. Yes, no, nobody cares. So 300 times 33.066. 330s. 300 should be. I don't know where the 30 came from. 300. There you go. Thank you. Times 33.066. Little hamster went home for the night a while back. It's giving us $9,919.80. That's the amount. But this is the amount of a ordinary annuity. We want an annuity due, so what are we going to do with that? Times 1 plus 0.05 divided by 1. Where did divide by 1 come from? Annually, once a year. It's the power of 1 because only 1 period, right? So times, parentheses 1 plus 0.05 divided by 1, $10,415.79. Yes. Now in this case, since the payments are done per year, that's a full year's worth of extra interest you got. Make sense? So let's look at some examples here. What is better? Over 30 years. $100 per month at 9% interest. Or $15,000 one-time payment at 7%. Well, let's take a look. Option A. When all else fails, guess A. Or true. 100 times, open, open, open. 1 plus 0.09 divided by 12, close, power of 360 minus 1. Close, divide, open. 0.09 divided by 12, close, and close. So that gives us 100 times 1, 2, 3. 1 plus 0.09 divided by 12, close, power of 360, minus 1, divided by open, 0.09 divided by 12, close and close. $183,074.35. Questions? Let's do the other one then. How do we do the 7%? I should put a compounded monthly here. Have to have a compounding factor on that to make it work. So how do we do the $15,000 one-time payment at 7% compounded monthly? Well, this is just a future value problem from last week, a compound interest future value. It's just going to be 15,000 times, parentheses, 1 plus 0.07 divided by 12 to the power of 360. That's the simple compound interest formula. 15,000 times 1 parentheses, 1 plus 0.07 divided by 12, close, power of 360. $121,747.46. So in this case, it wasn't really even close. That was for 30 years.
But I mean, you're paying in twice as much.
In 30 years, yeah, you are.
You're paying in 36,000 even, and you're getting.
You're getting back 183. Yeah, it is. You are paying in quite a bit more. Yeah. But you're going to pay it in over 30 years rather than all at once, too. I mean, how many people have 15 grand sitting around right now unless they just sold a kidney or something? You know? Inheritance. Yeah. People that save their money. Yeah. Those people don't exist. They're a myth. You think you save your money? Cool. That's good. Now let's take a look. Let's say that we have someone who invests $200 a month we're going to give them 8.5% for 40 years. And what I want to do is I want to find the equivalent single payment. In other words, if I'm going to start right now making this $200 a month payment for the next 40 years, or if I just want to make a single payment right now and get it over, not have to pay anything per month, what would I have to put in right now? So we're going to start out with the $200 a month and figure out what that future value is. So it's 200 times 1, 2, 3, 1 plus 0.085 divided by 12, close, power of 480 minus 1 divided by, close parentheses, then divided by, open, 0.085 divided by 12, close and close. So let's punch this in, see what we get. 200 times 1, 2, 3, 1 plus 0.085 divided by 12, close, power 480, minus 1, close, divide by, open, 0.085, divide by 12, close and close. 807, 730, 47. That is the amount that you would have if you made that $200 a month for 40 years. So now let's go backwards and find the equivalent single payment. That was the equivalent present value. So that's going to be the 807, 730.47 divided by, and we're assuming we can still get that 8.5%. So 1 plus 0.085 divided by 12, close to the power of 480. And that's it, because it's just a single payment. The only time we have to go through all this other junk is if we're making regular payments. If you have a single payment, it's just that simple formula from the last week. So we're taking that number divided by, parentheses, 1 plus 0.085 divided by 12, close, power of 480. Equals 27,281.63. So instead of paying $200 a month for the next 40 years, you could just pay $27,000 right now and you'd end up in the same spot. What do you think? Better than a sharp stick in the eye? What's that, sir? You sure? This is the part in the evening where I get to give you good news. We're done. Just because this stuff is so complex, if I gave you more, all I'm doing is pushing stuff out from the beginning of the period right now anyway. There's a new quiz due tomorrow, Wednesday, 11:59 p.m. New homework due tomorrow. Or not tomorrow, due tomorrow. The little hamster left the wheel a long time ago. Due next Tuesday, thank you.